So we're going to look at some more applications of vectors, and one of those will be closest distance. Okay, how's that? One of the applications. So let's say we got good old Theodore Tugboat. Everybody know Theodore Tugboat?
Yeah. What? Yeah. Theodore Roosevelt.
It's 4 kilometers west and 10 kilometers south of the harbor, which we shall call H. Moving with a constant velocity, moving with a constant velocity, represented by the column vector 24 kilometers per hour. Okay. So let us start by, you get all that? A, determine, which means what? Show your work. The position vector of Theodore relative to the harbor which is H, T hours after he sets off. So I thought, yeah, maybe it'd be nice if we could see a picture of this, right? Just have an idea. So you can do a rough sketch in your book, and I'm going to try this, bringing up a nice, sheet of grid paper here, and I've got him moving. Which way is he moving?
2, 4, so 2 direct, or 2 blocks. 2 right.
East and north. Okay, so we're going to stick him down in the corner, right? So here's Theodore's initial position, which is negative 4, negative 10, right? Because he's south. So that means the harbor must be 1, 2, 3, 4, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So here's the harbor, which is where? 0, 0, right? Okay, and we want to draw Theodore moving, so I'm going to do what? Go 2 positive x and 1, 2, 3, 4. So I'm going to put down a number of points, maybe even where they belong, but apparently not.
Apparently it's not calibrated.
Definitely not calibrated. So we will recalibrate.
Record the calibration.
We will record the calibration. Okay, so if anybody's wondering how to calibrate a whiteboard, see, it's when you lift the pen, so this way you get to move in. It's the one thing they did right in this user interface, if you ask me.
Is it better to draw on the whiteboard every single time you do it?
Okay.
Not the whiteboard. It's going to be
Although H was, okay, so 2, 1, 2, 3, 4. That's good. 2, 1, 2, 3, 4. 2, 1, 2, 3, 4. 2, 1, 2, 3, 4. 1, 2, 3.
I get it, which is why it's called closest distance, because it doesn't go to that. There's no point.
It's not going to the harbor. It's going to go by the harbor.
Runs into the harbor. Maybe it does, you never know. Maybe it runs into the lighthouse.
Okay, so there's Theodore's direction of travel, right? There's the harbor there. Which I suppose we should have labeled on the other side. So clean that.
Is the harbor part of the line?
No.
Look like it's on the line. If you did the math and said, hey, if I go 2 over and another 2 over and I go up 8, will I hit 0, 0? Not likely. I will, as a matter of fact, hit 0, -2, so no, it's not part of the line. Okay, what else? So what are we supposed to do? Determine the position of Theodore relative to the harbor. So we need a vector to describe old Theodore's position. So let's call that vector R1, which is equal to xy, which is equal to -4, -10, right? Plus t times, yeah, thank you, 2, 4.
I was thinking that.
Which is equal to, and, okay? So that's Theodore's position relative to the harbor at any time t measured in hours after he sets off, right? Okay, questions about that? We're good? Determine, which means what? Determine Theodore's speed. What's Theodore's speed?
Well, then bar
It's the magnitude.
yeah, that thing.
Yeah, okay.
Is equal to the
The
square root.
magnitude of the velocity vector is the speed.
Yeah,
And the velocity vector is?
The square root of 2 squared plus 4 squared.
Which is root 20, which is 2 root 5. It's good, see? That's the way radicals should be done, right? You see root 20, you write 2 root 5. Not a whole lot of thinking goes into it, it's just 2 root 5. That's 2 root 5. Okay, now, get that all copied down. Okay, let's move on. A lighthouse. And now we introduce the next character in our little drama.
Oh my god. It's almost like physics. There's a story now. It is physics.
A lighthouse L is 25 kilometers east and 13 kilometers north of Harbor H. Determine, which means what? That's right. We'll know that. Determine the position vector of Theodore relative to the lighthouse L T hours after he sets off. So, where is it? 2513, right? And I'm just, this is going to give us a nice scale drawing, right? I don't expect you to have that. You don't need the scale drawing in that, but then when we start to figure stuff out, these things will make some sense. Right? When we say, well, how far is it from the harbor? You say, oh, okay, it's not that far from the harbor, right? Based on the scale drawing. I suppose if you slap down a thing and really, is that number? So, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. 5, 1.
A long time counting.
Old-fashioned way.
How else are you going to count? Okay, so there's L at 2513. Okay. So, what is the position vector of Theodore relative to the lighthouse L?
So
So pretend this is now 0, 0.
Oh.
Then what's this point here?
A lot.
Okay, wait. I'm saying this point here.
29.
So now we are pretending that L is 0, 0, right? We are changing our frame of reference. Yes? So that the lighthouse, we want the position relative to the lighthouse. This now becomes 0, 0. So this is
Negative 29.
negative 29,
Negative 23.
negative 23. Okay? So we'll call that R2, which is equal to XY, which is equal to a position of negative 29, negative 23 plus T 24, which is equal to
Negative 29 plus 2.
okay. That's his position relative to the lighthouse. You plug in 0, 0, and you're at negative 29, or not 0, 0. You plug in T is 0, you're at negative 29, negative 23.
That's it?
No, no, no. Now I have to go to the previous page because I'm working backwards in this.
Oh,
Okay,
okay. Okay.
all copied down. Good. D. Determine. At which point you should all just be saying, show your work. At what times? This is like being in a church service, right? I say determine, and then the audience responds is, show your work. Right? Come on, you've all been to, you know, it's responsive reading. I say determine, they show your work.
That's not good. If I don't like how you the audience is always yell, show your work. That's not
At what time? No, you can just do it silently in your head at that point.
Oh, okay.
At what time and the position of Theodore when he is closest to the harbor. Okay, so we know from the drawing, which is very nicely done to scale, that he will not go to the harbor. Right? He's going to go by the harbor. How close will he get? What's the closest that he will get to the harbor, and when will he be there?
A 0, negative 2. No.
What?
Well, we,
No.
that's not the closest.
That's not the closest point.
That's not the closest point.
It's a perpendicular to.
It's a perpendicular to. So we go back here. The closest point is,
There.
yeah, it's even though it's drawn to scale, it's still kind of, you know,
It's still uncalibrated.
needs to sort of be
so-
blown up a little, right? So it's a perpendicular distance, right? Because the closest, you know, you did this in coordinate geometry, right? And you can actually do this with coordinate geometry, right? So you could be sitting here saying, oh, we just do this with coordinate geometry. Why are we doing all this vector stuff? Right? I mean, I know the equation of this line. I can work that out. And then I know the slope of the line. Well, we already know the slope of the line. And then I can get the slope perpendicular, and I can find a point on the line such that blah, 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 right? I mean, there's another line, etc. that's perpendicular to that line. And okay. And that's true, right? But it's less true when you get to 3 dimensions. And it's a lot less true when you get to 4, 5, 6, or 7 dimensions. Whereas what you work it with vectors, it really doesn't matter if it's a 2-dimensional, 3-dimensional, 4-dimensional, whatever, right? The process is the same in n dimensions. Okay? So that's why we're doing this. That's why you study vectors, right? It's not that, hey, I got easier ways to do this. I can just use coordinate geometry. Really, that can be done before you know. Okay? But then we go to a 3-dimensional, and you can still use coordinate geometry in 3 dimensions. It gets a little bit tougher. We go to 4-dimensional, and now it's really tough to picture because we can't do that, right? We don't work into 4 dimensions. So, all right. So,
Everything has to move.
so let's say that there is a point C on this line, which is closest to R1. So that, okay, so what I'm going to do, actually I might redraw this little section on here. Okay. So let's do that, right? So and then a T down here, right? T. Okay, that's what it looks like. And we know that's perpendicular, right? Okay, so there is a point C.
Shouldn't it be switched around, like C and H? Why? Because the Harvard code H,
On the line R1. So, OC. Oh, in this case being the origin, which really could be HC because the harbor is also the origin, but okay, which is vector C is equal to
0, 0. Wait, that's why.
yeah, but there's more. It's on this line, right? Any point on this line must satisfy -4 plus 2t and -10 plus 4t. Right? Remember, go back 2 pages.
Okay.
Back. Go back 2 pages. All points on the line R1. C is a point on the line R1. Okay, so it has a... Okay, back here. But OC, what's this symbol? Is perpendicular to R1. So, shift things down a titch. That means that -4 plus 2t and -10 plus 4t dotted with the direction vector of R1, which is 2, 4, must equal 0, because perpendicular, right, dot product, and the perpendicular is equal to 0. Which means, what? So -8 plus 4t
Equals 0.
minus 40 plus 16t. What's the dot product, right? It's times this. Right? It's u1 dot u2 or v1 plus, u2 dot v2. So it's this times this plus this times this. So it's minus 40 plus 16t is equal to
0.
Okay, so what do we got? -48 plus 20t is 0. 20t is 48. T better be positive, right? Because we are moving into the future. 2.4. Okay, so in 2.4 hours, right? Because t is in hours.
Now you have to find.
So, or maybe we should go with, therefore, in 2.4 hours, Theodore will be closest to the harbor. And what will Theodore's position be? So -4 plus 4 times 2.4? 2 times 2.4. It's off the screen. And then -10 plus
4 times
-10 plus 4 times 2.4, which is equal to something 0.8 and -0.4. Does that seem to match up with the diagram?
Yes.
Sure.
Yeah, because it's to the right of, which, 0.8 and 0.4, and that's 1, it's close. Like, that's almost halfway down, so,
Almost.
Wouldn't, look, I think this is off a tip, should be bit that way, but.
Hey, you didn't have a ruler.
Yeah, didn't have a ruler. And I didn't bother getting the straight line tool out, so. What? Oh, scroll up.
Here. Yep.
Oh,
Okay. And could we figure out how far Theo is from the harbor?
yeah.
How?
Oh, use the, yeah.
That.
Yeah, square root of blah blah plus blah blah. So how far is Theo from the harbor?
Square root of 0.8 squared.
Yeah. What? I'm asking Theo.
He actually wants to answer this time.
Let's see. Is 0.9
Okay, so 0.9. Yeah, I'm assuming rounding to the nearest tenth.
Yeah.
Okay. So he's 0.9 kilometers from the harbor, or 900 meters even. All right. Now, here we go. That was the penultimate. This is the ultimate, I think.
Ultimate?
I don't know. Was the ultimate the last one, or was the nadir? This is the zenith. That was the nadir. I don't know. Determine. Determine.
Show your work.
Ah, thank you. At least one. At what time? And what position? Theodore is closest to the lighthouse. Think of the first one as a special case, right? Which is really just how far are you from the origin. But now we're doing how far are you from a point. So we're doing the closest distance between a point and a line.
You can make the lighthouse the new origin.
No, I'm not going to. I have this written down. I'm doing it this way. So we know what? Gonna draw something that looks perpendicular.
We know. Eyeball.
Yeah, we'll see how close it comes up. So I'm going to call that, I don't know what to call that.
Point L.
Well, that's
P.
Oh no.
P, because it's a
I
point.
there's already L.
Now I got to transpose it. I wrote it down with a different letter in here, so I'm just going to get all messed up now, I'm sure. Okay, so the point is 2513, right? That's the point. Here's the line. Okay, that's the line.
Oh yeah.
Now what we're going to do is we're going to do this. We're going to draw some position vectors. Okay, so I'm going to draw the position vector here and call that L, because it's going to L. Lesson's going to L too. But, and then I'm going to draw this and call this position vector P, right? So they're from the harbor, which is actually the origin. They're from the origin, right? Position vectors are always from the origin. Okay, got that? So I got vector L, I got vector P, and if I want to go here, because that's where we want to go, then what's this vector here? Well, we got to get rid of the L, right? So L plus negative L, no L, plus P is P, right? That's why this one's negative L plus P. Got that? We're going this way. We're going from here to here. So I want this vector from L to P. This is vector L. This is vector P. This is negative L plus P. It's just adding, right? L plus something equals P. Well, you better get rid of the L, and you better add the P. So L plus negative L plus P, right? It's easier to do it in that order, right? Because you write it as P minus L, and then it's like, but this is L minus L plus P, which is just P, right? Gives you this. Okay, y'all got that? No? Okay, I have a vector L, you got that, right? Just a position vector, it's measured from the origin, which is H, should be O, I suppose, but, and it's here. And I've got a vector P going to some point, we know not which, right? Don't know where that is, but we know it's on this line, right? This is what we know about point P, it's on the line. You know, so was C, but it happened to be closest to the harbor. Where is point P? Well, it's on this line, okay? And we need this vector because this is the one we're interested in, right? Because we want to know where does this meet this. Okay. So if I'm going to do this, right, I want to do tip to, so I take L going this way and then this vector going this way, and that's my resultant, right, which means I'm adding, right? So I take vector L and I want to add this vector to it, and I want to end up with a P. So L plus something equals P. Okay? That something is negative L plus P. That makes sense now, right? Because the L plus negative L is going to be poof, and then we're just left with P. Okay? So that's the vector negative L plus P. Ready? Okay. Moving on. So what do we got here? So the line, oh God, everything's named differently. No. So the line L. So the point, okay, here we go. So the point is 2513, right? The lighthouse Lighthouse. 25 to the point. The point we're trying to find is closest to the line. Okay? Pay attention. The point.
I don't memorize it.
The line. What's the line? No, the line. This line.
The vector.
It's R1, right?
No.
What's R1? Negative 4 plus 2t?
Yeah, negative 10 plus 14.
Okay? Because it's the line R1 that we're interested in, right? Okay. Good. All right. So, what do we say? We're going to call OLHL. That really should be an O, right? For origin, base, just, translate it to. Do you want me to use O? Can I use O?
No.
Just for origin?
No.
Because it'll translate when you're doing other problems and you're not looking at H, you're saying, oh, O is the origin.
You'll make it easier for yourself when reading off the sheet. I know.
Oh, so, or 8 or O. So, O. Okay, origin. I'm going to use O.
Now it's basic, guys.
Okay, so OL, which is vector L, right, is 25, 13, right? Okay, just a position vector, okay? Oh, God, I gotta translate now every time. So LH, so LP, which is the vector negative L plus P, right? LP, okay, which we call negative L plus P, right? So what's negative L plus P? So, okay.
Oh my god.
Control plus C, no.
No, erase that.
I like how you left the top.
Okay, so it's negative 25, 13 plus because it's a point on the line, right? Okay, so remember, point P is on the line, and therefore is one of these guys, right? There's some value of T such that this is point P, yes?
Because
Okay.
it's governed by that.
Yeah, because it's on the line. Okay, so negative 25, 13 plus is, okay, now we can simplify that, right? Which is equal to, so negative 25 minus 4, negative 29 plus 2t. And negative 13 minus 10 is negative 23. Have we seen those numbers? Never seen negative 29, negative 23 anyway. Plus, oh, that was a different example though, so I'm sure they're not related. It's just coincidental.
He's lying to us.
Or not.
You can tell by his voice.
Okay.
Like, I sure.
Now we get into the fine print, right? So, and the dot product of, so, and the dot, extend the page, needs more. And the dot product of LP and the direction, right? It's the direction, and the direction of is equal to 0. Because they're perpendicular, right? And it's only the direction of R1 we care about, right? We don't care about anything else, it's just direction. So, LP, well, that's, okay, move down a bit. Negative 29 plus 2t and negative 23 plus 4t dotted with the direction, which is 2, 4, is equal to 0.
In this case, it's
You missed the dot.
So it's negative 58 plus 4t plus negative 92. We'll just go minus 92, right? Which is 4 times 23 is 92. Plus 16t is equal to 0. And we'll extend the page again. Okay, so what's that? Negative 100, negative 150. So we got what? 20t minus 150 is 0. So t is 7.5. So how long will it take? 7.5 hours. Where will it be? Substitute into what?
Oh, into the equation for t.
Negative t plus.
Let's keep extending the page. So after 7.5 hours, so the Theodore will be closest to the lighthouse after 7.5 hours. His position relative to the harbor is, okay, so what's Theo's position vector relative to the harbor? We did this somewhere. Relative to our negative 4 plus 2t and negative 10 plus. Okay, so negative 4 plus 2 times 7.5 and negative 10 plus 4 times 7.5. So what's that? Negative 4 plus 15? 11. And negative 10 plus 30? 11, 20. Which puts him 11. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. 1, 2, 3, 4, 5, 6, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20.
Oh, you are one
this
unit
is-
wrong.
Close. Well, if I'd have looked ahead, I could have put it in the exact right spot. Right? But
That would be
close.
cheating.
I didn't. Yeah, I know. So close. What's his position relative to the lighthouse? Oh, let's go to a new page.
Relative to White House.
The lighthouse.
So this is relative to the harbor.
That's relative to the harbor. Now, don't we have an expression for that? We worked out a position relative to the lighthouse. What was it? Negative 29?
Oh, plus 2t.
Or sorry, negative 24 plus 2t. And negative, oh no, sorry, negative 29, and then negative 23 plus 4t. So negative 29 plus 2 times 7.5, and negative 23 plus 4 times 7.5, which is what?
14, 7.
Negative 14, 7. Is that true?
You can check.
Well, so from 25, if we go 14, that'll take us to 11. If we go 7, that'll take us to 20. So, yeah, it'll take us to the point 11, 20, right? How far apart are they?
Just do the distance products, which is
See, which is, so why work this out? Because that's how far apart they are relative, or that's their x and their y position, right?
60 kilometers.
Let's put approximately equal to, it's not exactly 16, is it?
No, it's 15.65.
Let's go 15.6.
That's about enough.
Yeah, 16 is just too round. Round is the nearest 100, it's 0. They're on top of each other.
15.7.
Yeah, 15.7. It's 15.65.
Oh, wow. We'll never get there. Right, so it was useful to figure this out, right?
Yeah.
Okay, because otherwise we'd have to figure this out from here, right? And we'd be going 25 minus 11, right? And then we'd be going 13 minus 20 and squaring those, and, right? Because we then have to use the distance formula with these 2 points. But we got its relative position, which really just tells us how are you getting there, and then you can work out the distance from that. Okay, that's all I got.
Really?